Okay, good afternoon. My name is Tim Pakiak. I am the co-chair for the TAC Young Members Group, and I'd like to welcome you today to another one of our fantastic Tunneling 101 webinars. So today we'll be talking about the intro to the sequential excavation method, also known as the New Austrian Tunneling Method, or NATM, and it's also referenced as the sprayed concrete lining method. Okay, so before we get started, just a little bit about us. So the TAC-WAM group was created in 2014 as a platform for communication between students, young professionals, and mentors within the industry and with other member nations. So TAC actively creates opportunities for young professionals and students to participate in regional technical talks, regional and international young members webinar series, and field trips and site visits. So we have multiple active young members groups across the country, located in Vancouver, Toronto, Montreal, and Kingston. Just a couple of announcements. So we have the deadline for our undergraduate and graduate scholarships are coming up. So that'll be March 15th of 2024. Application for these scholarships can be found online at the QR code on the screen. And so the undergraduate scholarship is valued at 2,000 Canadian dollars, and it's intended for undergraduate engineers in the fields of geological or civil engineering, whereas the Dan Eisenstein Memorial Scholarship is valued at 6,000 Canadian dollars, and it is intended for postgraduate students planning to undertake or currently undertaking a postgraduate studies in the field of tunneling at a recognized Canadian institution. So if you'd like to get involved with the Young Members Group, you can reach out to us on Facebook at Tunnel Canada, Instagram at TAC_young_members, or send us an email to tac-ym@tunnelcanada.ca. So now I'd like to turn it over to Sinan alum. So Sinan was born and raised in London, United Kingdom, pursuing his education in geology and engineering from the University of Manchester. He has over 13 years experience in heavy civil and infrastructure design and construction, having worked on well-known tunnel infrastructure projects in the UK, such as the Thames Tideway, High Speed Rail, or HS2, and Crossrail on the contractor side. In his positions, he has been liaising with owners, representatives, the design teams, and integrated designs into the construction process and managed site logistics from commercial and technical perspectives. Sinan is a results-driven geotechnical professional whose expertise covers design and construction for public infrastructure projects, including many SEM shaft and SEM tunnel drives, along with segmented lined TBM tunnels. His career is based in delivering major construction projects, managing construction logistics, planning, staging, and ground-related risks. His achievements include successful completion of SEM tunnels and shafts across all of the Central Thames Tideway projects, sites, and 2 TBM drives over 12 kilometers in length in central London. After moving to Canada 2 years ago, Sinan joined Dr. Sauer and partners as a senior tunnel engineer and has been involved with several large subway extensions. Sinan, I ask you to share your screen now, and I will hand it over to you.
Okay, Doc. Bear with us. I'll just start my presentation. Okay. I think you guys can see that.
We're going to send it live.
Is that okay? We good?
If anybody watching can confirm that they can see the screen, just type a question into the chat. And then if it comes up, we can just confirm that. So.
Maybe, maybe not.
Yep. Okay. Fantastic. We're good to go. I'll pass it over to you. So.
Brilliant. Okay, doke. As Tim mentioned, my name's Sinan Alam, and this is an introduction to SEM. So just a little bit of background on myself. I know Tim already went through that spiel, but just to kind of go through what my history in tunneling and where I kind of came from. I'm not actually a civil engineer, like probably many of you on this call. I did a straight geology degree from the University of Manchester back in 2004. And I became like a geotechnical engineer for a couple of years for various employers, a few different, and worked onshore and offshore, which was for rigs and pipelines and things like that, doing seabed investigations. I then got married in 2011, and apparently it turns out it's not conducive to being married and then leaving for 6 weeks at a time to go to the Caribbean and things like that. So I then decided that it'd probably be better to be stuck in a tunnel for long periods of time to help that. So I actually joined the Crossrail project, and it just kind of happened to fall into my lap. It wasn't something that I was trying to get into tunneling at that stage. It just was a really, really big infrastructure project in the UK at the time, and they're recruiting like crazy. So I was like, yeah, cool, good to go. And to be honest, yeah, that's definitely where I started enjoying being in the tunneling environment. I was a SCL geotechnical engineer from 2012 to 2014 on the Crossrail project, and then I was a geotech for the HS2 project, which is a high-speed rail project going from London to Birmingham. And then I joined as a senior kind of geotech for the Thames Tideway project, which is like a super sewer project. So just to kind of give you some background on those, I'll talk a bit more about them later. But the Crossrail is about a 6.2 meter diameter tunnel with 21 kilometers length, and Thames Tideway is about 7.2 diameter, so fairly big sewer tunnel, and it's another kind of 25 kilometers length, and HS2 has sections which are almost 9 meters in diameter. Those are obviously the segmental lined tunnels, but there was a lot of SEM structures associated with them. And then in 2021, I moved to Canada and joined DSP as a senior tunnel engineer, and worked on a few of the big tunneling projects in Toronto so far. Seeing how these go. So just a bit of outline of this presentation. We'll go through some background on SEM, some principles and applications, some typical kind of geometry sections that would be used for various underground structures, whether they're tunnels or adits and things like that. The ground classification systems and support classes, so deciding on how you excavate and support the ground using those classification systems. Design considerations, instrumentation and monitoring to check what we're doing is correct and within the specifications, and things aren't going to fall down mainly. And some of the construction projects that I've worked on, so they are kind of London centric a little bit, but I thought we did some interesting stuff there, and some of it, or a lot of it, can apply to Toronto as well. So just to start from the basics, this is some terminology. We've got our kind of geometry, tunnel geometry here on the left-hand side, and then this is kind of like the cross section of the tunnel being advanced. Top called the crown, bottom called the invert. That is the face, so that's kind of the active area of where you're excavating the ground, going forward or driving forward the tunnel. A pre-support or forepoling is installed ahead of where you're excavating to try and protect your crown area. You also have, obviously, these are the pre-support elements that have already been installed in previous advances. The kind of depictions of the pre-support here show the different types of pre-support as well. So we can have just kind of bars, steel bars, or grouted. So you kind of see the ground around that one, for example, shows grout traveling out from these what's known as like a pipe roof umbrella. As a form of pre-support. And then kind of the linings, which is what we use to construct the tunnel. So the first lining is called the initial lining. And then we also have, if you have a large enough cavern or tunnel, you have separations and temporary walls and temporary inverts. So basically taking smaller chunks of the tunnel out before going and creating the full larger structure. Those are temporary because, yeah, they do get broken out, and eventually you end up with a case where you can install your waterproofing layer, for example, whether that be sheet membranes or sprayed on waterproofing, whichever is either specified or designed for. And then you have your final lining, and obviously the flat kind of math concrete inverts. That's not necessarily structural in most cases, but obviously required for general tunnel uses, whether it be road tunnels, subway tunnels, whichever. And the final lining is essentially what's going to be taking your final load cases, hydrostatic pressures, and things like that, and providing that 100-year design life. The initial lining generally is designed for a 5 to 10-year design life, but that can be adjusted as per kind of owner specifications. This is known as the round length. So that's quite important, which is specified within the design or adapted within the kind of res process, which we'll go through a little bit later. And what else do we have? Oh yeah, the kind of rock bolting or any other forms of holding the ground back. So that's what kind of these are specifying or trying to signify there as well. Terminology, Tim already mentioned it, can be called NATAM, New Austrian Tunneling Method, SEM, which is preferred kind of in North America, sequential excavation method. In UK and Europe, possibly more predominant to use SCL, spray concrete linings. We also have mined or conventional tunneling, shotcrete methods, observational method, etc. They all kind of apply to the same excavation process. And the main thing is differentiating it from a TBM or a pipe jack kind of method of tunneling. The definition kind of points to it being a cyclic construction process of excavation, mucking, and primary support, excluding TBMs. So the SEM is an approach based on a kind of design philosophy. So it's optimizing the self-support of the ground and economic excavation support. So we're aiming to not create over-conservative linings or extremely thick support systems. Is based on what the ground is doing or how the ground is in that specific location. And the instrumentation and monitoring is obviously a very big part of that, feeding back information into the excavation support systems that's going to be used. Sauer, who we worked for, once said, the main man himself back in 1988, said that a method, or SEM is a method of producing underground space by using all available means to develop the maximum self-supporting capacity of the rock or soil itself to kind of provide the stability of the underground opening. And I think that's a key thing in what we do in SEM, whereby we're using the arching effect of the ground, using the properties of the ground to support the tunnel, as opposed to trying to prop everything and push everything back as you would in a heavy civil cut and cover structure, for example. What NATAM or SEM is not is just a set of specific excavation and support guidelines. So I think it's important to kind of outline that not one size fits all. The design is very dependent on what exactly you're trying to achieve, what kind of space you're trying to achieve size-wise, and what the ground is telling you, and how the ground is going to react to that specific underground structure. So it's very specific to what we're doing, but also can be very flexible, and many different approaches used to achieve what the client wants, for example, in that underground space. We'll go through. Well, I'm not going to go too heavy on the history because I'm not a massive history buff with regards to SEM, I suppose. But what we can kind of focus on or see is that shotcrete or fast setting mortars and tunnel support has been used as far back as kind of the mid 1800s. Kind of mid 1960s is when NATM was kind of coined a bit more, or introduced to the general tunneling environment. There is some debate as to who might have introduced it first, and different countries always kind of claim different things, but basically it's been around a long time in Europe, and maybe not so much in North America, but is creating or becoming more prevalent as our kind of environments become more and more urban. We need to look at solutions which disrupt the surface less, and things like SEM and NATM essentially are the solutions that can be used. So some of the key principles: mobilization of strength, or optimize self-support of the ground. So we can kind of see the first basic principle: we excavate ground. The excavated ground kind of creates an arching effect. So we kind of remobilize or mobilize of ground strength is achieved by allowing kind of controlled deformation in the lining. So there's a stress redistribution, and it leads to kind of self-supporting ground or a stand-up time, which is then utilized to spray on your initial shotcrete and things like that. The kind of flexible support measures that we're utilizing has to lie in like a kind of key location on this kind of ground distribution curve. So we have displacement of the ground and support pressure that we're looking at, and you can either go really high with the support pressure and limit the displacement, or kind of go lower with the support pressure and have higher displacements. But essentially you want to find that kind of middle ground sweet spot. The kind of initial support is installed considering relative stresses and stiffnesses, and you need like a flexible support system rather than a rigid one. Otherwise it's going to end up just cracking and failing as the ground stresses redistribute. So whatever support is used is essential that it's placed and remains in physical contact with the ground and deforms with it essentially, and that's kind of the key element that trying to convey using the SEM method. Instrumentation and monitoring, obviously quite important to kind of get that feedback. SEM execution requires kind of a systematic data collection program, so attempts to quantify design assumptions and early indication of unexpected conditions as well. So as we're getting that feedback from whether it's monitoring the lining, whether it's monitoring the ground water levels in the area, deformations and things like that, you get an early indication of any sort of unexpected conditions, and that data allows for kind of performance monitoring and back analysis as well. So the designs as we go forward can be refined even within site on one project, or one project to another. You're able to always refine that lining thickness, or able to refine your geometries as you go along. So and also kind of depending on contractor agreements, data can provide justification for kind of adjusting the support requirements during construction, and I think that's a key element that SEM is flexible enough to do that, and we're constantly refining that method as we're going along. Ring closure is quite important. So as we're excavating the ground to create that full ring around, closing the invert kind of establishes that load-bearing ring. and a sequence of invert closure based on ground conditions. In rock, ring closure is obviously less critical as the rock has a better self-support mechanism. So you have typically flatter inverts, and the lining installation can be delayed as well. But in soft ground tunnels, ring closure is vital, and one of the things that was quite a historical almost event was the collapse of the Heathrow tunnel in the early 90s, and this diagram kind of shows how the invert heaved up and we lost the clay plug in the invert of the tunnel, which kind of then created this knock-on effect of all the other structures or sections of the lining closing in on itself and the tunnel collapsing. There's obviously lots of different lessons learned from that collapse, but one of the key findings is the mechanisms used for ring closure were not clearly defined or clearly followed by the construction team, and that kind of comes down to the crux of it. Like I said, there's a lot of different aspects. I don't want to, attempt to know exactly how you can quantify all of it and give a full rundown of that. But one of the key takeaways was that the ring closure wasn't clearly understood and wasn't adequately implemented in the field, and that created this invert heave and created quite a substantial collapse in that tunnel. Ground classification, that's something that is a key kind of element of how SEM tunnels are also designed and driven. So identifying kind of ground and design support categories and excavation sequences and subdivisions of the tunnel face is kind of based on those factors. So the ground conditions, the stand-up time, excavation equipment available, and mucking versus support time. The kind of curve that we get out of that is something that is quite key to when you're designing these tunnels, and that can be done using an empirical kind of method, not any kind of fancy finite model or anything like that. It's, a simple Excel sheet or hand calcs can give you quite a good curve as to how the ground is essentially going to react. So if you have your tunnel somewhere down here, then distance away from the tunnel center line, you can figure out how much the ground is going to deform and react to that appropriately, whether it be improving the ground or changing the geometry, or whichever way you're able to kind of ensure that settlement isn't an issue to the surface assets or any other structures adjacent to the tunnel that you're trying to build. Contractual agreements are quite a key element in the principles. It's an observational method, SEM, and that requires kind of flexible contracts to make design changes. So as you're building it, every day we have this meeting or process with a required excavation support sheet. So that's the red sheet, and that gives you the basic kind of information that you need to go ahead and start creating that tunnel in the ground, essentially. That meeting every day with the kind of designers and the contractors, engineers are key to understanding what's going on down in the tunnel, and if there are any major changes that need to be kind of addressed with the design, and there is quite a lot of flexibility there. So temporary excavation support measures can be adjusted based on the ground conditions, and past and upcoming activities are reviewed along the monitoring data. And I think that's key to how we build these tunnels. They're not built in isolation. We don't just have a set of rules. Like, as we're building them, we're reviewing data, and that's feeding back into the system for the designers to consider how we can ensure that we don't have any adverse reactions or issues in the tunnel, but also at the surface and on adjacent and kind of important assets. So for that to work, then cooperation with the designers, contractors and the owners is quite critical to resolving issues, and often the contracts have to be written and agreed like that. Applications, yeah. So this this image that we see on the right here is from the Blackfriars shaft and connection to a TBM tunnel in central London. That whole project, the Thames Tideway project, was all done within the river, so that's why we see this this structure going around the outside, which is a cofferdam. So they drive a bunch of piles into the riverbed and then drain the water out on the inside. That's the roadway or embankment, river embankment next to it, and then create this this shaft going down. So yeah, there's a lot of different. I think just within there you see a shaft, and on that project we saw many kind of different structures that we built with SEM, and I think a lot of times people just associate them with kind of large transit stations, but there's many different applications that SEM can be used, and ideally is probably one of the better solutions for them as well. Especially in kind of challenging ground conditions, complex structure as well. Like I know a lot of times that seems like that's maybe what is not conducive to SEM, but if the design is kind of looked at correctly and you have experienced kind of engineers, then it's definitely a method that can be utilized for all of that as well. Typical elements within an SEM tunnel, the geometry, so flat inverts are usually associated with rock, round invert usually associated with soft ground, initial ground support. We're looking at shotcretes and reinforcement, temporary if in the temporary case. Then you have the waterproofing system, drained versus undrained. So that's essentially whether you have a tank system whereby the waterproofing goes all the way around the tunnel and tries to keep all water at bay. Often that ends up being a scenario whereby gaps might be found and water somehow manages to make its way through, and we try and mitigate that, or the waterproofing guys try and mitigate that using regroutable sections or compartmentalizing the tunnel sections as well. And then a drain system obviously includes kind of an open waterproofing system whereby drains are included towards the invert or towards the bottom of the tunnel, and they lead off to sump pumps and areas like that, so that the water can be discharged through that way. And then you have the final ground support system, which is usually cast in place concrete, and that's the permanent. So it takes the full load case for full hydrostatic pressures, for example, and needs to usually kind of provide a design life of 100 years, which is what we're normally working to at the moment. That's just the finished case. Ground classification systems. I think there's a lot of different ones for rock, for example, RQD, rock quality designation, the Q system, the RMR system, the tunnels classification, which is more for soft ground. I think for all of these, it's quite important to understand that the system basis, how what exactly we're measuring, and the limitations before using them for a tunnel design exclusively, for example. What you're getting out of the ground from geotechnical investigation compared to what these classification systems are telling you based on that could be a bit different, and it's important to kind of make sure we understand that before we fully implement all of those. The geotechnical baseline report, so those are project specific support systems. The geotechnical baseline report, I think, is something that needs to also be carefully read and understood, not necessarily something that is always used or exclusively used for the design phase. Usually there's subsequent reports, interpretive reports that are more specific to the structure that you're trying to build to understand the ground. So basing everything just on the GBR can sometimes be problematic or dangerous because of the possible wide variety that you get in the GBR. But yeah, again, that's down to each project, and can't really have a blanket statement to say that. But yeah, it's the main thing is to be kind of cognizant of what exactly we're using and why we're using it. The Tunnelman's one is one that I'm fairly familiar with. Used a lot in the soft ground in London, and you basically have kind of these different ground classifications based on how the ground is going to react. A lot of these are then related back to the type of design requirements you might have. So yeah, essentially probably quite useful for the ground in Toronto as well, the soft ground, the glacial till and things like that. Yeah, it remains to be seen if that's the only one, depending on the specific site or location that you're looking at. Excavation methods. Drill and blast, very popular for rock, hard rock, possibly to soft ground as well, but typically used for mining applications. Not typical in urban areas, just because it involves a lot of dynamite and noise and vibration, etc. Generally, you see kind of this type of setup with a road header used for moderate to weak rock, which we kind of see in Toronto a fair bit with the shales. This particular bit of equipment we used a lot in London, maybe not with this kind of attachment because that's more for the weak rock. We had a lot more clay in London, but it was this conveyor belt system is very handy as it saves a huge amount of time. The ground or the spoil is lifted up through the middle of the machine and just constantly deposited into your piece of whether it be a dumper truck or whatever is able to be waiting there to be loaded and taken away straight away, and just have that turning around constantly and get a pretty good advance rate going from that. And usually that's what it boils down to: advance rate equals money, and we can kind of see that a lot of that analysis has been done. This is the net cutting rates against compressive strength, and you can kind of get an idea of how much you'd be able to get out of the road header, depending on what the ground is telling you or the lab testing is telling you for that location in particular. Tunnel excavators, look like normal excavators, but have a few key and fairly expensive differences. The one being this kind of swivel action that you see, so the arm can articulate in much more different ways to what you'd see on a regular backhoe or JCB at the surface. Also, a lot more protection for the hydraulics due to the application of the machine, and the adaptable hydraulic connection as well is very important. You might be doing kind of different things within one tunnel drive, whether the ground conditions change or if you move that machine over to do a platform enlargement whereby you're taking out TBM segments. You need to be able to change that head so that you can do that, or the bucket, etc. Because trying to lift up the entire machine and put in a new machine is time consuming, costly, all that kind of stuff. So little things like that are key to keeping your SEM excavation going quickly and smoothly. Photos. Yeah, I think these are all from the mine stations at Aggington. Some really impressive work that was done there. I haven't been able to go down and see that much of that yet myself, but a lot of the guys that we worked with have a good amount of experience coming out of those mine stations that were done on that Centers project. Design considerations, again, ground support interaction models. So what the failure mechanism of the ground is essentially going to be. So stress redistributions is in ground resulting in transferred loads. So you need to address potential failure with design elements. So subdivision of the face, pre-support, ground improvement, and essentially in rock we have these kind of wedge and stress induced or squeezing and swelling actions. What are the in situ stress levels, the confinement, the rock mass characteristics, etc. But in soil, we're essentially looking at the water content and the groundwater table, moisture content, obviously, and whether it's cohesive or granular material is obviously quite important. Trying to decide on what the stand-up time could be or how we divide the face is all dependent on those factors. The diagrams that you see here are essentially talking about the face support or face stability analysis and these kind of failures that you could get from a wedge or a silo effect that you get coming into the tunnel, and that's quite important for how you end up designing your ground support. Empirical analysis. This is done through classification systems, ground loads, and the associated recommended support systems. You also get the volume loss from an empirical analysis. It's using the rock mass quality and rock support classifications, which many of you probably know fairly well, with the amount of rock into Toronto or Canada. The advantages is that it's very quick and cheap. Using something like an Excel sheet or whatever, you're able to kind of predict loads and displacements quite easily. But the limitations include no ground support interaction and the assumptions that you're making and the way it's extrapolated, etc. So yeah, limitations, but at least you get a good initial pass at what the ground or volume loss could be from the tunnel that you're proposing. Numerical modeling is also something that's obviously used a lot now. You have all various different methods, boundary elements, finite element models, finite difference models. The main advantage is it simulates the construction sequence, can model kind of complex ground behaviors, and account for other structures in the area. So modeling in other assets, for example, whether that be utilities or an adjacent building, basement and things like that. Those are kind of what people or clients and the construction team need to see in order for them to give them the confidence to go ahead and excavate whatever tunnel that you're proposing. The main limitations, though, is it's very costly. Time and the software, I suppose, and some of those assumptions and simplifications can introduce complexities almost just as you kind of make assumptions that aren't necessarily true to what's happening in the real case. 2D modeling and 3D modeling. I'm not going to profess to be a massive modeling expert, but I do try and understand the kind of limitations and where they're used. So 2D for typical sections and linear structures, and 3D is essentially should be or ideally used for junctions and intersections and complex geometries. Convergence confinement method and stiffness reduction. Yeah, these are again items that's used to get that 3D effect. Whether they are fully or can be fully relied upon in all cases is something that has to be assessed on a case-by-case basis. Where we go? Okay, yeah. So I think we're and moving on. So I think it's good to get on to some of the examples of work that I've been involved with. So Crossrail is a job in London. It's 21 kilometers of running tunnels, 8 underground structures in kind of a busy, really busy urban central London environment. Initially had a budget of 15.9 billion. What the end budget was is probably still being debated. One of the stations that I worked on was Tottenham Court Road, and this is the kind of format of the station, and these are a bit more typical of stations built in London, kind of like a ladder station, as they sort of call them, whereby you have a central concourse tunnel, which then has kind of small adits at different positions along the tunnel to lead up to your platform tunnels themselves. And the platform tunnels were created in SEM as well, along with all of the other tunnels that you see here. Some of them included fairly complex geometries going above and connecting into the platform tunnels for ventilation, escalator tunnels and things like that as well. So yeah, a fairly interesting job. One of the main kind of considerations for these tunnels were invert heave, because of the fact that we were predominantly in London clay, but we had a water-bearing granular strata very close to the invert in some locations. So there was a lot of depressurization requirements put by the designer to check all of these locations and drill basically underneath to ensure that we either create a depressurization pathway for the water to escape, or that we're just checking the ground ahead of where we're about to tunnel. The Thames Tideway Tunnel, that is one of the most recent projects I was involved with. That's 25 kilometers of running tunnels, TBM, running up to 65 meters below the River Thames. The section that I was kind of responsible for was this area here. So fair few sites. There's 21 sites all together all the way along the river, and it's basically trying to control the most polluting combined sewer overflows by intercepting them, storing, and conveying the discharge, which currently flows into the river. So this was a little bit of background on one of those sites, which is just. You can see it from here. It's kind of, yeah, that one. Sorry, that one right there. The Albert Embankment site. Again, these are all built into the river, so we have these cofferdam structures which are driven first. Then the inside of the cofferdams are drained out. We have 2 of them. The main TBM tunnel goes under the River Thames, and then we have these new shafts which are built in SEM as well, and then a connection tunnel created to discharge those flows from the river overflows. So generally these shafts are connected to the overflows that come normally into the river. So they intercept those, drop them down, and then send them down the main TBM tunnel. This one had quite a few structures, an interception chamber, and the tunnels that were done here, the connection culvert and the connection tunnel as well, were all done in SEM. For this particular site, we made our own geological model because we had a lot of different geological information, geotechnical information from different sources. So we tried to find something that we could combine all of that and create a model that would help us with the SEM works that could be utilized in the res process as well. So this was kind of going through the basics of that geological model. Not necessarily that relevant, but yeah, the main things here was that we were essentially using the face maps that were done in the tunnel, the probing ahead, and feeding that directly into the model every day. And essentially what we came up with, these discrete boreholes that were represented each advance that we did, and then that essentially created a geological cross-section, which could be essentially created daily because it was done through the modeling software. Kind of future applications of that, we were looking at incorporating the utilities in the road, and then putting that into the geological model and seeing how the settlements through the volume loss of either the shaft or the other structures would affect that. Blackfriars is another site along the Thames Tideway corridor, which I worked on. Again, a cofferdam, but this time, instead of having any connection edits or anything like that, the SEM shaft, which was built, essentially intercepted the TBM tunnel and drove right through it. So we had this kind of situation whereby we had initially created jet grout columns that were protecting the SEM works in the water bearing strata, and then below that we had a section of clay, and then the SEM shaft is driven all the way to a few meters below the base of the TBM tunnel. So this is again a fairly sizable TBM tunnel, 7.2 meters, I think, internal diameter. And yeah, just a few kind of photos of that, how that took place. So you can see the TBM tunnel in the background there once we've driven kind of past it. And all of this kind of stuff on the walls had to do with dewatering elements as well that were put in. These grout streaks are from the jet grout curtain that was put around the SEM shaft, so we could safely excavate going downwards. Again, yeah, just some more photos to try and kind of show you we can see the two TBM tunnel sections either side, and them kind of working their way through that and trying to get down to the base. One of the main considerations for this shaft, and I think that's another key thing, is that we sort of associate SEM with just tunnels only, and obviously there's a lot of examples of tunnels, but shafts is another big kind of process or structure that's used a lot in London. Possibly helps with having the London clay having a good stand-up time, but this shaft in particular was driven into a very dense water-bearing granular strata right at the base, and so dewatering for this was very important. There was a lot of very highly sensitive assets in the area, and if the dewatering was to fail whilst we were still installing or driving the shaft, which obviously takes months in itself, then there could be a situation whereby a lot of those assets would be adversely affected. The gas mains that were 50 years old or whatever that supply large sections of the banking district of London, for example, sewer mains, other very important utilities, and also the Waterloo and City line, which was another big subway that ran across that. Okay, sorry, my monitor says it's going off. Anyway, so we did a lot of modeling of the groundwater situation, and had to check a lot of the different stratas which contained waters. A lot of it was kind of artesian or water that was in between two aquetards, essentially. This is the dewatering dashboard that was used on a daily basis to try and check how the water levels were reacting. We had to do a lot of in-shaft dewatering as well. And all of this kind of feeds into the SEM process that we wanted to use in order to build this shaft. This shows this was actually shows the jet grout curtain that was put around as well, and a fairly sophisticated model was put together on that Monte Carlo statistical model to try and figure out if there were any gaps in the jet grout curtain, so that we could ensure that tunneling could occur when, or sorry, the shaft could be driven downwards as we get through the water-bearing strata. Sorry, so this had to do with essentially the redundancy in the system, which was needed in order to ensure. So the chalk wells, we had chalk underneath, granular strata, and then the water-bearing chalk underneath that shaft, and yeah, essentially there had to be a huge amount of independent redundancies for ensuring that the dewatering, if one system failed, then another system would kick in. So yeah, back to kind of other tunneling applications. We kind of have the geotechnical baseline report. This is an example from Avenue Station in Eglinton, and again, it's important to kind of keep in mind how these are created and the overall picture that you're getting from them, as opposed to maybe specific areas that you're looking at for construction of an SEM structure. General station configuration in Canada. This is a 3D rendering of that, and we have like a nice little 3D render of the construction stages. So the TBM running tunnels, you have generally a head house, which now we're looking at doing in SEM as well on some projects, because the circular shaft it can be a more economical way to drive those structures. But yeah, creating a crosscut coming out of there, which intercepts the two TBM tunnels, and then the caverns going either side from there. Design considerations, I think instrumentation and monitoring is quite important. Trigger alerts for your various assets need to be considered. The res meeting daily, this is kind of a nice little graphic of who the people that are involved that need to weigh in on the res meeting, and it's quite important for a res meeting to have the right people there to give you the right information and make decisions within the meeting as you're tunneling away. These are other examples of the res sheets and items that you have on them. Obviously, the area that you're tunneling at the time, and then pre-support measures, excavation numbers or sequence numbers, and things like that, to kind of make sure everyone's aware of what's coming up in the coming days, weeks, months, whatever. Pre-support, these are some really good photos and some good depiction of the pre-support elements in the crown used for the mine stations on Eglinton. Excavation methods, as you saw, this is the Liebherr 924. The size of the machine needs to be compact enough to get in between those two temporary drifts, but also strong enough to excavate and reach what you need to get to as per your design requirements for stepping the face, etc. That is the road header that we mentioned before, with the conveyor belt in the middle. Face mapping, very important for confirming or checking the ground conditions as you're going along. Contractually, it's usually has to be done every advance on any of the projects that I've worked. Some of the contracts here might be different, but yeah, generally you're looking to identify any changes in ground as you're working to feed that back through the res process and change any design considerations or design elements that you need to as you're working through them. Shotcrete, few kind of variations in shotcrete. The fibers that can be used, the design of the fibers, the material of the fibers, the accelerator. So that's obviously as the name suggests, accelerates the setting process of the concrete. So it also then reflects on the strength of the concrete. So there's a bit of a balancing act there to ensure that you have concrete that has the required compressive strength. Applications, the ceiling layer and face support and the initial lining, temporary support walls, all of these will use the shotcrete method, so that due to the flexibility and time it takes to apply them. There is rigorous QA QC as you're applying that shotcrete. It needs to be tested. Slump and air and temperature penetrometer tests are done for an early indication of the strength, especially if you need man access to a certain area which has been sprayed with shotcrete. And then further to that, lab testing is done for structural and compressive strengths in the long-term basis to achieve the 28-day strength, for example, or other design milestones. These are some pictures just from a crossover that I was part of on the Crossroad project. The kind of sequencing for these type of tunnels is quite interesting as well, whereby the platforms are essentially enlarged and then you drive smaller drifts along the side to create a crossover tunnel, which then links to the other running tunnels. So yeah, definitely something that is easily or more flexible using the SEM technique, and definitely creates a lot less disruption to what, especially here, was a very, very busy, congested urban environment. This one I just thought was a cool excavator. I used one of these to do an escalator drive. Yeah, all the legs kind of articulated. I think, to be fair, it's mainly used for like ski lifts and things like that, like in Austria. But I think someone thought it'd be a good idea to do an escalator drive with it, and we were all for it. It looked very cool. It was very, it was useful, like, because it was quite an inclined drive, as you imagine some of the escalators are nowadays for the deeper stations. And yeah, the jumping in that, the inside of it looked like the Starship Enterprise. To be honest, so many buttons. It was bit of a dream. Lovely. Waterproofing. It's just a nice picture from the mine stations. You can kind of see the water bars and barriers that are used to kind of compartmentalize and restrict any leaks that are coming into the tunnel. And then this is some final lining photos from again the mine stations. I think definitely one of the big things of coming to North America is these large caverns are definitely more prevalent as opposed to things like the ladder stations that you'd see in London and SEM. And yeah, they make for great photos, to be fair. It looks very impressive. Again, we can see the nice finish on the final lining here, and the arch formwork and everything on the mine stations. A lot of effort goes into creating quite a nice finished product. Shotcrete final lining, not something that I've been fully up to speed on, just I haven't been on site with it, but obviously done a lot of reading and design analysis on that, and definitely something that's going to become more and more prevalent in the future, I'd imagine. And I think that's about it. Yeah, thank you for listening to me ramble on about SEM, and yeah, if anyone has any questions, I don't think I can end my slideshow. Is that right, Tim? It's probably, I need to keep it up there.
Yep. If you just want to keep that slide there, that's awesome. It's a good looking slide, and there are some questions. So the first one that I have here is, for the collapse of the Heathrow Tunnel, you said a key element of failure was a lack of understanding and proper execution of ring closure. So what do you mean by ring closure, and as an action or as a noun? Completion of support elements, example shotcrete in the right location, or inadequate time?
Oh, okay, yeah, let me just go back to that photo for that slide. I think I can find it quickly. So yeah, maybe, yeah, apologies, I didn't explain it as well as I should have, but essentially, as you're driving these tunnels, we can kind of see from here that you do these top headings, for example, and you have to have some area for the rest of the tunnel to be driven as well. You generally drive the top headings ahead of the benches and inverts, and that creates your stability for the tunnels as you're going through. The ring closure element is essentially creating that entire ring that you would get. So these larger tunnels, whereby you're excavating smaller sections of it, the ring closure is the entire ring that you get, whereby you finish off and connect up the last portions of the tunnel. And essentially it's this kind of area here whereby they were trying to, I don't know if it was shortcuts or like I said, a kind of misinterpretation of what the design was trying to achieve, but this element here whereby the final part of the invert needed to connect up and create the kind of full arching effects wasn't done properly, essentially, from what the report says, and that's where you get that failure of whereby you have these stresses coming down, kind of redistributing around the tunnels, and essentially if as they're pushing inwards, that invert location becomes very, very important to construct properly, and so if that hasn't been done properly, or if there's a connection there that wasn't looked at carefully, or if you end up driving too many of the top headings first and not coming down and closing that ring, then you end up with a case where instability can occur and you get this invert heave. And I think basically a lot of those things all happened in parallel for this Heathrow tunnel collapse. It was one of the first major uses of NATAM in London, or SEM in London, and I think it was one of those learning curves that unfortunately had to be was a result or created like this situation where we had a fairly bad tunnel collapse, but then brought about a lot of measures to ensure that didn't happen again. So yeah, it is what it is, I suppose. But yeah, I hope that sort of makes sense.
Yeah. So we're gonna go from Heathrow to Toronto. Have you done any SEM in Toronto area? And if so, what is the average stand-up time for glacial till, or the soil you've excavated through?
So far it's quite there isn't that much, like that. And I think that's the key to North America and Toronto, is that there's a lot of tunnels now that are going to be built, and there's a lot of stuff that we're excited about, but it's been so long since some of the last projects. Glacial till wise, I have worked in some stuff similar in outside of London, but no, I haven't actually excavated the glacial till in Toronto. DSP is part of the cross passages on Eglinton West Extension, and those cross passages, I've been down to those a few times, and a lot of good work there, managing the shale and the water ingress in the shale, which is quite important. And the glacial tills is similar. It's non-cohesive predominantly. It's a mixture, which is very important to keep in mind, and the water content as well. So I think ensuring that that you have a lot of toolbox and support measures available if the ground changes, which it inevitably will, and managing the water are the key issues there. Stand up time wise, it's very dependent on water content and what exactly the ground is in that location, and with the variability that you get, there are locations, I think, whereby the stand-up time could be better because of the clay content, but I don't think that it's going to be anywhere near as good as the nice London clay that we see for all of these kind of large infrastructure projects in central London.
Okay, that makes sense. So the next question I have here is, Have you had an experience where the excavation support plan had to undergo a major change because of observations and instrumentation and monitoring indicating a problem or better than expected performance?
I think better than expected performance is usually down to TBM drives, SEM drive wise. In London, I think generally it's because of the London clay. It's just down to the methods and means that you're using to get that clay excavated and supported. So it's a well-known medium. So people have been kind of advancing various techniques. But for the other side of it, the instrumentation and monitoring has definitely helped to identify problems early. Convergence, we've seen a lot of times in tunnels indicating possible weaknesses or ground-related issues, which then we change whether it be advanced lengths or we do more probing or we increase dewatering efforts, and that's definitely been the case in a few of the tunnels that we've driven in London, especially with the River Thames just above us as well. So yeah, the monitoring definitely has always played an important part, and if anything, even if it's not directly for the tunnel, we're doing more and more tunnels in very, very urban environments. It's absolutely imperative to ensure that you're not affecting your next door neighbor or destroying a gas main or whatever. Like, you know, those are just as important as the tunnels that we're driving. So yeah, the instrumentation and monitoring is definitely an early indicator for that, and is key to ensuring that you have a successful tunnel drive.
And keeping on the theme of changing and adjusting support, the question here is, who has ultimate responsibility and decision-making power to change or to adjust support in the RES meeting?
Yes, it's a good question, I suppose. I think generally there should always be an senior SEM engineer who holds the res meeting, is either part of the design or appointed by the designer's representatives, or appointed by the designer themselves, and I think ultimately, you know, I think the buck kind of stops with them to a degree, just purely because the interested parties, the angle that they're looking at it, right? From a constructor's point of view, a lot of times cost, time, and effort is prevalent in their decision making. The owner's point of view is a massively over conservative design sometimes, so that they can ensure that no assets are affected, or you end up with a tunnel whereby you're essentially not going to get any sort of settlements or cracking or whatever inside the tunnel. And then you kind of sit in the middle as maybe the SEM engineer to balance those two items and ensure that you are looking at cost, you are looking at time, but you're also looking at the finish that you're trying to achieve in that tunnel. And yeah, I would say that's an important kind of aspect, but definitely not just something that should be decided by one person. The res meeting is essentially because all of those people are there, and they have to be kind of all involved in that process to make sure that all the information is considered.
Okay, fantastic. So we're going to move to the next question, which is, what would you consider a watertight? What would you consider a watertight tunnel? Would you always expect some leakage at the end? And can you have a tunnel with no leakage?
I think that's naive to think that tunnels will not ever leak. I think it's managing leakage is the key. I've worked in London clay for a large part of my career, which is a very homogeneous, lovely, perfect aquitard. And as soon as you put a tunnel in there, just water starts appearing, right? So I think it's you know what I mean? Like, I don't think anyone can ignore that fact. Water finds the path of least resistance, and to assume that there's never going to be any water turning up there is a naive design assumption, in my opinion. And instead we should be designing planning for when water does arrive, and if anything, and if that degrades our lining or degrades our tunnel in any way, you know, it's better to look at the long term and think about how we can tackle that, as opposed to just assuming that we've built everything perfectly. And a lot of times it has nothing to do with how you build it, but how the ground is reacting to that structure, and how it could be possibly changing. The water table itself is impacted by various things. We did a lot of water modeling for that Blackfriars shaft, for example, and the influence zones and how the water migrates and things like that, done by really kind of high level hydrogeologists. It's a whole other ball game, and to kind of think that we're going to deal with something that isn't going to affect that is not really, I think, the best design assumption. So yeah, I think it's always deal for water, hope for the best, and if you don't get any water, happy days. Kind of.
I think that's a really good piece of advice there. So there's quite a few people on the call, and there's obviously lots of interest in SEM and NATM. Do you have any recommendations on textbooks, manuals, guides for those getting their start in tunnel designs for SEM in particular?
Yeah, there's Alan Thomas book, I think, which is one of the Bibles. Forgot the name of it. There is also some books, specification books from the BTS, the British Tunneling Society, published like some really good stuff. Yeah, I think I could have a think and pull out some names and maybe like send them to you, Tim, if you want to send them around or something like that. But yeah, off the top of my head, I think like being in a tunnel is like the best way to learn. To be honest, I know that's not easy to say, but like I think whether you're a designer, whether you're part of the owners representatives, whether you're on the construction side, just getting in the tunnels and seeing how they build them, how the support measures work, how the ground reacts to the tunneling is, I think, key to being a better tunnel engineer. Maybe I don't know. Like, yeah. So yeah, I would say maybe have a look at some of the BTS stuff, and there's a lot of information on from the UK side of things, because it's just used there almost exclusively.
Okay, awesome. Yeah, if you send me a few names and a few really good guides, we can definitely throw that up on social media or into the magazine or something like that. So that'll be fantastic. That's all the questions that I have here in the chat. So I think we'll end it there, as we're about 1:15 here in the Eastern Standard Time Zone. I'd like to thank everybody for attending this Tunneling 101 webinar. Sinan, thank you so much for being with us here today to present. I'd like to let everybody know that this presentation has been recorded, and we will be putting it up on TAC's YouTube channel. So I've posted the link into the chat if you would like to go see this one again after we've put it up, or if you would like to rewatch any of the other Tunneling 101 webinars, please go check out the page. With that, I hope everybody has a great rest of their day, and stay tuned for more information about the next upcoming webinars, about potential site visits, and for any local events happening at the chapter level. So take care, everybody.
Cheers.